In this webcast, we're going to take a survey of different types of aromatic heterocycles that we have yet to discuss. First, we're going to talk about fused ring systems, move on to two-atom heterocyclic systems, and multi-atom heterocyclic systems. First, let's take a look at furan and thiophene shown here. So furan and thiophene are related in structure because sulfur lies directly below oxygen on the periodic table and thus has a similar electron configuration to oxygen. If we look at the two pictures of the sulfur and the oxygen, we see that each are sp2 hybridized, each have two lone pairs. In each case, one lone pair occupies a p orbital that contributes to the pi system and the aromaticity of the molecule, and the other lone pair occupies an sp2 hybrid orbital perpendicular and away from the ring. If we move on and look at the resonance stabilization energies of these different compounds, if we look at thiophene, pyridine, pyrrole, and furan, and compare them to the resonance stabilization energy of benzene, we notice that these heterocyclic systems don't have quite as much resonance stabilization energy as benzene. Although you don't need to memorize the data in this table, it's just worth noting qualitatively that these heterocyclic systems are not quite as stable relative to the benzene system. As we all know, benzene is quite inert to many reactions. Therefore, the heterocyclic systems may not be quite as inert to certain reactions. If we move on and take a look at fused ring systems, first we'll take a look at benzofuran here. Benzofuran is basically benzene fused to furan ring. If we move on and take a look at this indole structure, this indole structure is the most important out of all 5 of these fused ring systems because it makes up the side chain of the amino acid tryptophan, and its substructure is benzene fused to a pyrrole system. Now it's worth noting, because indole here is the side chain of an amino acid, it's worth noting why we're studying these heterocyclic compounds to begin with, because they show up so frequently in bioorganic reactions and biomolecules, and we need a good grasp of these before we begin to study these reactions of bioorganic reactions and biomolecules later in the semester. So if we move on to these fused ring systems, we see benzothiophene here, which is basically benzene fused to a thiophene ring, and move on and see quinoline and isoquinoline here, which only differ in the position of the nitrogens. Here we have two-atom aromatic heterocyclic systems, and we have 2 different classes shown here. The first class is the azoles, or azoles. Of these 3 structures, we want to key in on the imidazole structure. The imidazole structure is the most important out of these 3 because it makes up the side chain of the amino acid histidine. If we move on and look at the diazine structures, again we want to key in on the middle structure, pyrimidine. Now pyrimidine is the substructure of nucleic acid base pairs, and these, as we all know, are critical to the functioning of life at the molecular level. If we move on and take a look at here a multi-atom aromatic heterocycle, and we have the structure of purine. Purine is rapidly in equilibrium between these 2 structures here, shown right here, and both structures are in fact aromatic, and we could make a quick count of pi electrons if we needed to confirm that. So in this slide, we're given, this is an old test problem, an exam problem, where we're given the structure of guanine. Again, we see a multi-atom fused heterocyclic system. So the first part of this problem says to draw all the lone pairs in the heterocycle. So if we remember that nitrogens want 3 bonds and 1 lone pair, and oxygens want 2 bonds and 2 lone pairs, we can quickly fill in all the lone pairs on the guanine structure as shown here. The second part of the question asked us to consider all the pi electrons in both rings and how many pi electrons are there in all. And note, we're not just concerned with the pi electrons on the ring directly. We need to consider the pi electrons of the atoms appended to the ring. So if we know from our connectivity diagram shown from previous webcasts that a 2-connected nitrogen only contributes 1 electron to the aromatic system because the lone pair is in an sp2 hybrid orbital and not conjugated to the ring, and that 3 connected nitrogens do contribute both electrons in the lone pair to the aromatic system, we can make a quick count of all the pi electrons. If we start here at this nitrogen and make a count of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pi electrons for the core of this structure. And again, we need to consider the atoms appended off this molecule. So the oxygen is double bonded, so it contributes 1 electron, 1 pi electron also, so that would be our 12th electron. And the 3 connected nitrogen bonded down here is also has its lone pair in a p orbital and would account for our 13th and 14th pi electron count here. And the third part of this question says circle all the electron lone pairs that are involved in pi bonding. So if we remember again that 2 connected nitrogens, their lone pairs are not involved in pi bonding because they're in sp2 hybrid orbitals, and the 3 connected nitrogens, their lone pairs are involved in pi bonding because they're in p orbitals. We can quickly circle all the 3 connected nitrogens because they're involved in pi bonding.